One of the first things that comes to mind when I think of playing AAA games is the incredible animation of characters. Not just during cutscenes, but also during gameplay. How can we start to achieve this seemingly AAA level of quality for our own smaller indie games? The answer that we'll explore today is procedural animation. In this tutorial, you'll learn how to create the subtle environment interactions that you may have seen in popular third-person adventure games. We'll start with an initial setup of our project, and then we'll break down an actual example from Uncharted. We'll learn all about state machines, and then finally go through step-by-step programming the environment interaction state machine. By the end of this tutorial, we'll have an awesome procedural animation, and hopefully you'll have learned a lot along the way. This project is over a year in the making. I'm not going to ask for you to do it now, but if you do learn anything over the next hour and a half of this tutorial, please consider hitting that like button to help share it with the rest of the game dev community. If you don't know me, my name is Nikki. Welcome to iHeartGameDev, my channel all about game development. And now, let's get started. In today's Unity project, we have the character Banana Man making its infamous return to the channel. Banana Man can be downloaded for free directly from the App Store. Banana Man can stand, walk, and run. All three of these animations are keyframed animations, meaning they are static and always look the same. We'll be learning to make procedural animations, which are dynamic animations that change based on specific conditions or parameters while the game is being played. And in this project, our procedural animations will be programmed to have our character interact with specific objects in the game environment. Let's start by downloading Unity's animation rigging package found under the Unity registry section of the package manager. This package provides components that make procedural animation much easier because they interact directly with Unity's built-in animation system. Let's use this package's components to set up our character. Taking a look at the hierarchy window, we can find and expand our character game object. Notice the hierarchical list of the character's bones, also known as an armature. Using the rigging package's bone renderer component, we can visualize each individual bone in the armature, displaying the character's full skeleton. Here's the fastest way to set this up. Select the root character game object in the hierarchy window, then navigate to the animation rigging dropdown and press Bone Renderer Setup. We can immediately see the character's bones rendered in the scene view. With the root character game object selected, the inspector now shows the bone renderer component with a pre-filled list of all the character's bones. If you notice any bones are missing, simply drag them from the hierarchy onto the top of the transforms list, then disable and re-enable the component for them to show up. Why is this helpful? The bone renderer component makes it much easier and faster to select each individual bone instead of the character's 3D mesh. This will help us as we build the character's rig and decide which parts of the character we want to procedurally animate. And what is a rig, you ask? As simplified as possible, a rig in Unity is a collection of bones and bone constraints that are used for animating the character. And constraints determine how specific bones can move and rotate. Let's add our first rig to our character, and we'll use the fastest method to creating one. With our character selected, let's open the animation rigging menu again, and this time, press Rig Setup. Here, a couple things happen. A rig builder component attaches to our character. One of its fields is preset to a new child game object titled Rig1. Rig1 has a rig component attached to it. So Rig1 is our first rig. It will allow us to procedurally control individual bones of our character. But to actually create our procedural animation, we'll need to apply constraint components between bones and other objects, and add required code. We'll handle that later on, but it's important to understand the hierarchy of this setup. The rig builder is attached to the root game object alongside Unity's animator component. The character armature with all of its bones is a child of the root. We create new rig game objects for each procedural animation we want to make, which are also children of the root. Typically, each is named for its general purpose. For example, target tracking. Child game objects are then added with the constraint components necessary to create the procedural effect, and code can update the constraint values. As long as the rig is set in the rig builder, its constraint and weight values will reach Unity's animation system and interpolate between, or completely override, any keyframed animation values based on what it receives. To quickly summarize this initial setup, we now understand the difference between keyframed animation and procedural animations, and are now rendering the character's bones and have our first rig. The only remaining components before we can procedurally animate our character are constraints and the code. If you're looking for an even more thorough explanation and introduction to procedural animation before continuing on with environment interactions, all of this and so much more is broken down in my original Introduction to Procedural Animation. Now, to understand the foundation of our project, let's rewind to what first sparked this idea. A few months ago, I was playing through Uncharted 4 when I noticed the main character, Nathan Drake, would occasionally reach out to touch the environment around him. What was most impressive was that Drake's hand never clipped through anything, no matter how close to the wall I tried to get him. The game would simply adapt the hand and arm position based on the character's distance from that surface. It looked so natural, and that can be one of the major benefits that result from procedural animation. Let's analyze these procedural environment interactions from Uncharted. We'll see if we can learn anything from a deeper look at these near-perfect animations. Here we have Drake walking around a market that's found in the game. Watch as we have him approach certain pieces of the environment. What stands out to you about this procedural animation? After seeing it a few times, you might notice that despite the animation being procedural and dynamic, there are consistent steps that make up the animation. Let's break them down. Step 1. Drake moves around the environment normally until he comes within a certain distance from an interactable object like a wall. Step 2. As Drake approaches the wall, the procedural animation system is triggered, and it begins to override the character's keyframed animations. He raises a hand in the direction of the object about as high as his waist. Step 3. When Drake is within arm's reach of the wall, the hand is raised to a higher position at about shoulder height, and reaches to touch the wall in the direction that he's moving. Step 4. After a short period of time, the hand position stops moving forward while Drake's body begins to move past it. And that leaves step 5. The procedural hand position moves back to its keyframe position. The overriding procedural animation deactivates, and there's a time delay before the whole system can restart. With all 5 steps combined, it makes up the complete animation. However, the interesting thing about this animation cycle is that it is not guaranteed that each step will happen. Ideally, the character will walk by the wall without stopping, and each step of the full animation cycle will be completed. We can consider this to be the best case animation cycle. However, several factors may trigger the character to break from the animation early, skipping to step 5, which resets the character back to keyframed animations. By experimenting with the game and testing this hypothesis, we'll find the 4 triggers that reset the animation cycle are as follows. Trigger 1. If the character stops moving. Trigger 2. If the character starts moving further away from the wall and the distance between the character and the surface increases. Trigger 3. If the surface ends and there is nothing left for the character to touch. And trigger 4. If the angle between the character and the point of contact on the wall no longer make sense. For example, the arm never reaches across the character's body. Okay, so we have a 5-step cycle for the full procedural interaction animation. We also have a list of triggers that will reset the animation at any point during the cycle. How do we go about programming this relatively complex list of animations? Originally, on my procedural animation livestream, we had started to fit all of the logic and code into a single class, and that might be your first thought as well. But it quickly became clear how overcomplex a single class can and will become. We need a way to break down the animation logic into smaller, more manageable chunks of code. Enter the state pattern and state machines. One of the most popular design patterns in game development, and my personal favorite that has been featured here on iHeartGameDev. The state pattern allows us to separate logic into individual states which contain code only relevant to that state. Now look at our animation list. We can consider each step we listed before as its own state. Naming each according to its purpose, we have the search state, the approach state, the rise state, the touch state, and the reset state. Here is a mockup showcasing the full implementation of the state machine model that we'll build together. The environment interaction state machine consists of the following classes: abstract classes, the base state, state management class, state manager, and the environment interaction state. The 5 previously mentioned concrete state classes, a context class, environment interaction context, and a concrete state management class, environment interaction state machine. Now that we have a clear picture of what makes up the environment interaction state machine, let's take a moment to explore the code foundation of a reusable state machine. Here is a summarized pseudocode example of a player state machine I designed a couple of years ago. What happens when we want to make another state machine with different states? We end up rewriting a lot of the same code. Over the next 10 minutes, I'll show you how we can abstract the core pieces of a state machine so that we can reuse them over and over again and keep our code dry. We'll start by creating a new folder titled State Machine. This will house 2 scripts, Base State and State Manager. Opening Base State first, this is an abstract class, which means that it's more of a blueprint or contract for other classes we program at a later time. Here, we will list all of the methods that each concrete state will have access to. Today, the base state will declare enter state, exit state, update state, get next state, onTrigger enter, onTrigger stay, and onTrigger exit. By marking them as abstract as well, any class that inherits from the abstract base state class will also have to define the logic of these abstract methods. For now, we'll have all of these methods return void, aka nothing, except for getNextState. GetNextState will return what's called a generic. Let's talk about generics. In C#, generics allow us to define a class or method with a placeholder type that is later replaced with a specific type when the class is instantiated, possibly inherited, or method called. We can declare a generic type using the angle brackets and a placeholder name such as t. Generics make our code more reusable by allowing us to create components that work with various data types. But it does so without sacrificing type safety or the need to create duplicate code for each type. What's cool is that we can also add constraints to the generic type. Using the where keyword, we can specify that the type must implement a certain interface or inherit from a particular class. In the case of our base state class, we can declare a generic type eState with the constraint where eState::enum. This will specify that eState must be an enum type. Now we can use eState as the return type of getNextState. We'll use generics a bit more in the State Manager class. The State Manager class acts as the brain or central controller of a state machine. The State Manager maintains references to all states, oversees the active state, facilitates transitions between states, and calls essential methods such as enter state and exit state, update state, and various triggers among others. State Manager will be another abstract class because it will allow us to create an unlimited number of concrete state machines. By deriving from State Manager, the concrete state machines will inherit this core state machine functionality. Again, we want this to be reusable. State Manager inherits from Unity's mono behavior, granting it access to methods such as awake, start, update, and the trigger and collision callbacks. We'll utilize some of these methods to get the state machine up and running, and also to delegate some functionality to the current and next states running in the state machine. Okay, our State Manager will store all of the concrete states of the state machine in a dictionary. Dictionaries are key value driven, meaning we give it a specific key, and get the value stored behind the key in return. In C#, we need to specify the type of both the keys and the values when declaring the dictionary. If we are going to store each concrete state as the dictionary's values, we can use our base state that we just defined, including its generic, as the type. What that means is that the State Manager class will also need to expect a generic enum upon instantiation. As for the key type, let's use the eState-enum itself. Now, the State Manager will create an instance of this dictionary. And because the only classes that should have access to this dictionary are those that inherit from State Manager, we'll set the access type to protected. In state machines, the active or current state refers to the state whose logic is being executed at a given moment, while the other inactive states remain dormant. Declare the current state, which will have the type of base state with the eState generic. Then set the access type to protected for the same reason as our state dictionary. Let's move on to the methods. The typical flow of a state machine in Unity is designed around the mono behavior lifecycle methods. Start is called once. In parallel, a state's enter method is also expected to be called one time. Let's begin there. Add the start method and call enter state on our current state variable. Then we can do the same for update state, which would be called an update, allowing current state to perform its logic on a frame-by-frame basis. Remember our base state's list of methods? We can implement the 3 trigger callbacks in mono behavior methods of the same name. In each, we'll pass the current parameter down to the current state's invocation. But hang on, we'll get an error because base state's onTrigger methods aren't expecting this argument. Luckily, we can quickly update and fix it by changing their abstract declarations. With the 2 remaining methods in the base state, getNextState and exitState, let's not forget one of the primary roles of the State Manager, which is to manage transitions between states. While we haven't added the definition for getNextState yet, we do know that it will return an eState-enum. This means we can add the logic here in the State Manager regarding transitioning from its current state to a new state, the next state. In the update method, we'll set a new variable, nextStateKey, equal to the return value of getNextState, and then add a condition. If the nextStateKey is equal to the current state's stateKey member variable, then update the current state. On the other hand, when these stateKey values are not equal to each other, a new method, transitionToState, is called to initiate and handle the state change. However, we will quickly get a couple of errors. The first stating that currentState.stateKey does not exist yet. Open the base state file to add the base state constructor. It will expect an eState argument called key. Now we can declare another member variable, stateKey, of type eState. In the constructor, set stateKey to the key argument. Now, whenever we create a new instance of a state, it will require that we pass and set an enum associated with it. Then we can use it in situations like our update method. Awesome. Now we just need to define transitionToState. When states change in a state machine, the exitState method is invoked on the active state, allowing it to perform any necessary cleanup logic before moving to the new state. Afterward, the new state is activated, and that state's enterState method is called to initialize any required state-specific logic. Then, the transition is complete. In our code, we'll create the new transitionToState method in the State Manager class. This will expect an eState parameter appropriately titled stateKey. Now, we'll perform the transition by calling exitState on the current state, changing the current state value to the next state by indexing into the state's dictionary using the stateKey, and calling enterState on the new current state. One thing we need to consider is that transitionToState is being run in the update method. meaning once per frame. We would never want this to be called in a different method and have transition to state simultaneously running more than once. We should fix that. Creating a Boolean member variable is transitioning state. We can set it to true at the top of transition to state method, and back to false at the bottom. Now we can set this additional condition inside of update. Wonderful. We have our base state and state manager set up as the fundamental building blocks of a concrete state machine. The major benefit of this implementation is that we can leverage these abstract classes and generic to create a seemingly endless number of state machines. Each state machine can define an enum list, which can then be used as the argument type to the state manager's generic. What that means is that the states have to be included in the state machine's enum. It's so clean and type safe. The framework for our state machine is now in place, so we can shift focus to the next crucial element, integrating procedural animation using constraints that are found in the animation rigging package. The animation rigging package provides a list of roughly a dozen different constraint components that can be applied on a rig. We can combine multiple constraints on each rig in order to get the procedural animation that we are looking for. Over the next roughly 10 minutes, we'll set up our character and project with the rig constraints needed for procedural environment interactions. In our project, we have a game object titled Rig1. Attached is a rig component. Start by renaming the rig to Environment Interaction Rig. For environment interactions, we want to take control of our character's left and right arms and hands. To accomplish this, we are going to use the two-bone IK constraint. Create two new children, left arm and right arm. Then attach a two-bone IK constraint component to each. IK stands for inverse kinematics, which essentially means that joints are positioned and rotated based on a target position. To set up the two-bone IK, we only need to set the tip property. Lock the inspector, then press on our character's hand bone in the scene view to highlight it in the hierarchy. Drag the hand bone game object to the empty tip property and find the small drop-down menu. When we select the auto setup from tip transform, every property will automatically be assigned. The left hand bone remains set as the tip property, while the mid and root properties are assigned to the left forearm bone and the left arm bone. But now we also have source object properties. Look at our left arm game object in the hierarchy. There are two new children, left arm target and left arm hint. These are set as the source objects. The target is the point where the tip, or in our case, the hand, is going to try to move. And the hint is used to specify the direction the limb should be oriented when it bends. It's worth noting that this automatic setup works as expected with traditional bone layouts, like Banana Man's. One bone for the upper arm, one bone for the forearm, and one for the hand. If it didn't work, you could try setting this up yourself manually. Before we preview the procedural animation, we're going to want to visualize these two source game objects. To do so, select each and in the bottom right of the scene view, press the plus icon to select a mesh. This transparent mesh is only visible in the scene view, but makes working with the source objects so much easier. Repeat the same steps for the right arm game object to set it up for procedural animation. Once complete, we can now activate the procedural animation override by doing one of two things: entering preview mode in the animation window, or entering play mode. Now we can see that as the rest of the character's body is controlled by its keyframed animations, the hands and arms are being overridden, trying to procedurally place the hands where the target is positioned. As we move the target around, the hand will follow. For the environment interaction rig, we're going to set default positions. We'll want the hint game objects to be placed at about waist level behind the respective arms. This will give the forearm and arm bones the most realistic rotation as the hand repositions itself. As for the default hand positions, we'll place them at about the same level in front of the character. Now, as we increase and decrease the weight of the rig, we can see the procedural animation from the 2-bone IK constraint overriding the character. However, if we go through the trouble of programming the movement for the target, we wouldn't get the desired result in the character's current state. Notice how the hand position is pointed fingertips forward. When touching a surface, our hands are naturally palm forward. How can we rotate the character's hands in addition to the repositioning from the 2-bone IK? The solution is to add more constraints to our rig. The multi-rotation constraint rotates an object to match the rotation of its source objects. Start by resetting the left arm and right arm target's rotation to 0. Add a multi-rotation constraint to the left arm and right arm game objects. For each, set the hand as the constrained object and keep all 3 axes checked. Then, use the target game object of the 2-bone IK as the source object for the multi-rotation. Remember to do the same thing on the opposite side. There is a good chance that by default the hand is not rotated in the direction that we're hoping for. To ensure that we get the procedural animation results we want, we need to update the offset setting. In the case of Banana Man, the left palm aligns with the Z forward direction when rotated 90 degrees on the y-axis. And to align the right hand, it needs to be rotated minus 90 degrees on the y-axis. This offset value is for Banana Man, and there is a chance that other characters require different offsets. Just be sure to align the palm of the hand with the z-axis of the respective target. Then rotate these left and right targets so that the z-axis is pointed in the forward direction of the character. Basically, the palm and the target should both be pointed forward. With those set, the hand will rotate to match the rotation of the source game object. Now in play mode, as we update the weight of the rotation constraint, the hand will fluctuate between the override from the 2-bone IK and the override of the multi-rotation constraint. With the weight at 100%, as we rotate the target, the hand will rotate as well. Once we have our character set, that completes our rig for procedural animation. The left and right arms will now follow as we move around the targets, and the hand will rotate to match the target rotation. We are now finally ready to program the procedural animation. In our scripts folder of the asset window, we'll see our state machine folder that contains the state manager and base state scripts. Create a new folder in the scripts folder titled Environment Interactions. We'll add 8 new scripts in order to implement our Environment Interaction State Machine. Those are named as followed: Environment Interaction State Machine, Environment Interaction Context, Environment Interaction State, Approach State, Touch State, Search State, Rise State, and Reset State. Open the Environment Interaction State Machine. The Environment Interaction State Machine class will derive from the State Manager class set up earlier. What this means is that the Environment Interaction State Machine inherits the definition set up in the State Manager abstract class, which actually includes the monobehavior methods. Notice that State Manager requires the generic eState enum type. We can finally implement the enum type that both our State Manager and base state expect. Inside the Environment Interaction State Machine class, we'll declare an enum, environment interaction state. Then we'll list out each of our planned states that will be a part of this state machine: search, approach, rise, touch, and reset. The E that precedes environment interaction state is standard naming conventions for enums. What this now allows us to do is pass environment interaction state machine.environment interaction state as the state manager's generic type. Based on the implementations of our state manager and base state, current state and the states dictionary can only consist of classes that derive from base state that use this enum type. And the state keys of each state can now only be set to one of these 5 enum values. Otherwise, Unity will throw an error. Next, let's provide access to all of the components of our character. To do so, add the animation rigging namespace at the top of the file. Now we have access to types related to animation rigging. Declare serialized fields for our constraint components. Left IK constraint and right IK constraint will both be private and of type 2-bone IK constraint. And left multi-rotation constraint and right multi-rotation constraint will also be private of type multi-rotation constraint. For environment interactions, we will need access to the character's speed and collider. For this project, Banana Man moves using a rigid body and capsule collider. Create two final serialized fields, rigid body of type rigid body, and root collider of type capsule collider. Note, if you are using the character controller, that is totally okay. You'll replace any logic surrounding the rigid body and capsule collider with equivalent logic for a character controller. We're really only accessing the speed from the rigid body and the dimensions of the capsule collider, which should translate fairly well. But if you have any questions, leave them in the comments or jump into the channel Discord, and this amazing community can definitely help debug. Back in the Unity editor, let's add the environment interaction state machine script to the environment interaction rig. Going forward, all of our logic will be impossible without these serialized fields being properly set in the inspector. In Unity, we can ensure that property values are set with what's known as an assertion. The assert class offers an array of methods that we can use to validate our code, checking conditions like whether a particular object is null, whether a value is within a certain range, or whether two objects are equal. If these conditions are not met during runtime, Unity will halt execution and display an error message, allowing us to quickly locate and fix any issues. We can access assertions through the namespace unityengine.assertions. Let's create a new method titled validateConstraints. We'll use asserts is not null method for each of the members variables we just defined. The second argument is the error message that will be thrown, so we can add helpful context explaining what went wrong. Now we just need to invoke our validateConstraints method. We can do so in the awake method of the environment interaction state machine. We can test this validateConstraints method by entering play mode. We'll see that the left bone IK validation currently throws an error, meaning it stops execution of the rest of the script. To fix all the validation errors, we just need to fill the references. Drag the left target and the right target into the appropriate slots. Unity will automatically extract the reference to the attached component. Do the same for the character's root game object to get the references for the rigid body and collider. Entering play mode, and the errors are gone. Our character now has its rig set up for environment interactions. Let's turn our attention back to the code and programming the environment interaction state machine. A state machine is designed to manage states, including creating and storing instances of each. Our State Manager class implementation does so using a dictionary to store state instances behind associated keys. Environment Interaction State Machine will create and store instances of all 5 states listed in its environment interaction state enum. To do so, we'll need to define all 5 of these classes. But if we look at our wire mock, we'll see an intermediary abstract class between our base state class and each of our concrete classes, environment interaction state. Let's implement this class. Environment interaction state is another abstract class that inherits from base state. Remember, base state, like State Manager, requires that we set the generic eState type upon inheritance. We can pass the environment interaction state enum that we set up as a part of the environment interaction state machine. This indicates that the classes that derive from environment interaction state will all inherently be associated with the 5 enum states of the environment interaction state machine. You may be wondering why this class exists when we already have the base state class. We've designed base state and State Manager to be modular and reusable. This intermediary abstract class allows us to define methods and properties that can be used across all of the 5 states. But wouldn't make sense in states from another state machine that also inherit from base state. Now, state machines have the concept of context, or a shared object that holds relevant data that can be accessed by multiple states. The context serves as a communication bridge between states, allowing them to share data and maintain consistency as the state machine transitions from one state to another. For example, the states of the environment interaction state machine are all going to need access to the 2-bone IK constraints, multi-rotation constraints, and rigid body that the environment interaction state machine currently declares. While we could store and provide access to these properties directly from the state machine to each state, a cleaner implementation is to separate concerns from the environment interaction state machine. State machines are more focused on state setup and management. Instead, we'll hand off the responsibility of these shared values to a separate context file, environment interaction context. Open the environment interaction context file. In order to hand off the responsibility of the variables from the state machine to the context, let's copy and paste the member variable declarations. Then the context can expect and set the value of each in its constructor. Now these are all private member variables, but when states need to access them from the context, we can create public getter methods for each. Getter methods mean they can look at the value but cannot change them. In our environment interaction state machine class, we can create a new member variable, context. After the validation method in awake, we can set context equal to a new instance of environment interaction context. Then we'll pass in the required constraint and rigid body arguments. However, the context will still be inaccessible to the states. How can we provide guaranteed access to the context for all of the state machine's concrete states? Our abstract environment interaction state serves this purpose. While it wouldn't make sense to have the context variable in the base state because the class should remain as generic as possible, this abstract middle layer between the base state and the concrete environment interaction states is perfect for declaring a protected variable that all inheriting classes require access to. Let's declare a protected context variable and have it set in the environment interaction states constructor. This means when each concrete state is instantiated, it will now require context to be passed as an argument. The base state class we're using also has a constructor expecting an eState enum on instantiation, which is used to set the state key. Environment interaction state will also need to expect this eState state key, so that it can pass it through to the base state parent. Remember, in this state machine, the state key will have to be one of the 5 environment interaction states. With this initial setup for the environment interaction state, we can begin coding the 5 concrete states. Each state will derive from environment interaction state and have a constructor method that expects the context and its associated state key. Similar to the environment interaction state, the constructor will actually pass these arguments to the parent classes using the base keyword. Concrete states are also required to implement the abstract methods they inherit. Temporarily, we'll create blank methods for each. As we go through and build out the procedural animation code for each state, we'll update these empty methods with the missing logic. Okay, we are now at the point where the concrete states can be instantiated. In the environment interaction state machine class, create a new method titled initialize states. This method will be in charge of adding the states to the state manager dictionary. We can add a state using the dictionary's add method. Let's start with reset state. First, pass the enum associated with the state, in this case, reset. Then, we'll set the value to an instance of that state. Each concrete state now requires the context to be passed in, and a state key. Pass the stored environment interaction context. Then, thanks to the generic applied to the environment interaction state, we can now provide one of these 5 environment interaction state values as the state key. So again, pass the reset enum to complete the instantiation. Repeat this process for the remaining states. Finite state machines like ours are designed to focus on one state at a time, hence the current state member variable in our implementation. We've now created instances of each concrete state, but current state has not been set. As the last step in initialize states, let's set current state equal to our newly created reset state. Index into the dictionary with the reset value of the environment interaction state enum. Now, we can just call initialize states in the awake method to set up our states whenever the state machine is enabled. With how we've set this up, the environment interaction state machine will start off with the current state set to reset state, and will be running the reset state logic. To test if this implementation works, we can add a log from the enter state and update state methods of reset state. Entering play mode. Success! Our environment interaction state machine is officially running. With our state machine up and running and our reset state set as our default state, we can now focus on detecting nearby objects. Let's take a look. Our environment interaction procedural animation is going to work by detecting objects that are close to our character. There are technically many ways that this can be done, but for our implementation, we're going to use a single collider that remains in front of our character at all times. While we can manually add a collider and adjust its size, there's actually a way that we can programmatically create a collider for our procedural animation purposes. In the Environment Interaction State Machine class, create a new method titled Construct Environment Detection Collider. For our project, the collider's width should equate to roughly the wingspan of our character, because that is the furthest the character's arms will be able to reach. Let's create a new float variable titled Wingspan. A character's wingspan is typically very close to their height. This means we can set the wingspan variable equal to the root collider's height property. It's worth noting that this method does assume that the root collider is set up correctly to match the character's height. Using the add component method, pass the box collider type specifying the type of component we want added to the environment interaction state machine. Then set the collider's size property equal to a new vector 3, passing in the wingspan variable for x, y, and z. The collider will now be set to what I determined to be an appropriate size for detecting the environment. Placement of this environment interaction collider is also important. If we invoke this new method in awake and test in play mode, we'll see it default to a 0x, 0y, 0z local position. However, using the wingspan again, we can find the correct placement. Set the collider's center position equal to another new vector 3, passing in the root collider's center x position for the x value, the root collider's center y position plus a quarter of the wingspan for the y value, and the root collider's center z position plus half of the wingspan for the z value. Using the root collider's x value means that it's centered with our character. Using the y value plus the additional 25% of the wingspan will elevate the box collider roughly an arm's height off the ground, and setting the z value to 50% of the wingspan will push the collider forward so that the entire collider is directly in front of the character. The last property to update before the collider is complete is the isTrigger property. Setting this value to true will remove physical collisions, and instead have the collider trigger events when interacting with other colliders in the scene. We'll use this to detect when our character is close to interactable objects and update our procedural animation. And remember, our base state declared abstract onTrigger events. This trigger will now call each. Testing in play mode, and we can now see that the collider is created on the environment interaction rig game object. The collider is positioned directly in front of the character, and it's able to pass through other objects because it's a trigger. Perfect! Now, if you're not getting the same results as we are here, maybe due to abnormal proportions of your character, go ahead and remove the code and manually add a trigger collider to the environment interaction rig instead. With the initial setup of the state machine complete, how will the environment interaction actually work? In the environment interaction state machine, when the character gets close to an object, the trigger collider placed in front of the character detects the collision with the object. By utilizing trigger events and other built-in methods in Unity, we can determine the closest position on the object's mesh where the collision occurs. As the trigger continues to intersect with the object's collider, we can continuously update this closest position. Simultaneously, we adjust the position of the inverse kinematics target in each environment interaction state, based on the distance between the character and the object. When the trigger exits the collider, we remove the closest position data and reset the IK target to its default position. Let's focus on how we can calculate the position from the character to the collider. Each state in our state machine implements the onTriggerEnter, onTriggerStay, and onTriggerExit methods. And our State Manager Abstract class calls these monobehavior-based methods with the current state. onTriggerEnter is called when the trigger first intersects with the new collider. onTriggerStay is called as long as it continues to intersect with the same collider, and onTriggerExit is called when they no longer intersect. These methods all provide access to the collider that the trigger intersects with. In our abstract environment interaction state class, we'll create a new method, getClosestPointOnCollider. It will return a vector 3 and expect a collider, intersecting collider, and a vector 3 position to check. Colliders in Unity expose the method closestPoint. GetClosestPoint on collider returns the value of intersecting collider calling closestPoint and passing in the position to check. Okay, we have a method that returns the closest point on the collider, but what is it closest to? What should we pass as the position to check argument, and where should we actually use this method? We will invoke it in a couple of places, and you'll see why in a moment. The environment interaction state machine consists of 5 states. Some of them perform the exact same logic in the onTrigger callback methods, but some of them don't. For example, the reset state won't have any logic in onTrigger enter, stay, or exit, because the state's purpose is to reset the state machine. Meanwhile, the approach and rise state may both require the use of getClosestPoint on collider, as we track and update the IK target position where we want our character's hands to move. One of the most famous principles of programming is to keep your code dry, aka don't repeat yourself. While we can't have the environment interaction state define logic for all of the states in the onTrigger enter, stay, and exit methods, because as we just explained, those might be different depending on the state, we can instead expose new methods in this abstract state that the concrete states can inherit and choose to invoke in onTrigger callbacks. Let's add 3 new methods to the environment interaction state. Start IK target position tracking, update IK target position, and reset IK target position tracking, all of which expect an argument intersecting collider of type collider. We can use these methods to call getClosestPoint on collider, and this allows states to individually decide if they want to use each method. Getting back into the weeds of our procedural animation, an important step for our machine is to evaluate which side of the character is closer to the target, the right or the left. This is important because it dictates which 2-bone IK, multi-rotation constraint, and IK target values are updated by each state throughout the animation. Fortunately, we can reuse our getClosestPoint on collider method to help find which side to use. In the context file, we'll create 5 new variables: current IK constraint of type 2-bone IK constraint, current multi-rotation constraint of type multi-rotation constraint, current IK target transform, current shoulder transform, both of type transform, and current body side of type eBody side. All of these variables are public but have private setters. Now let's define eBody side. eBody side is a public enum nested within the environment interaction context with right and left values. We've added all of these variables. Now to set them in a new method, setCurrentSide. This method takes a vector 3 parameter named position to check. By utilizing the stored left and right 2-bone IK constraint in the context, we can determine the side that is closer. Using the vector3.distance method, we can compare the distance between the position to check and both of the character's right and left shoulders, determining which is closer. In the case that the left is closer, we set the current body side, current IK constraint, and current multi-rotation constraint to the eBodyside.left enum, left IK constraint, and left multi-rotation constraint values, respectively. And if the right is closer, we'll do the same for that side's values. Outside of the if conditional, we can set the current shoulder transform and current IK target transform values to the current IK constraints root and target transforms. At this point, those are correctly set to the right or left side. Now, in our environment interaction state, we can use setCurrentSide to determine which side should perform the procedural animation. We'll want to do this at the start of the procedural animation flow, aka when our constructed trigger collider first intersects with another collider. Let's establish here that start IK target position tracking is the method that we can expect to pass to the onTrigger enter methods of each state that should use it. And with that agreement in place, we should use setCurrentSide in this method. Context.setCurrentSide is passed a vector 3 closest point from root. That is set to the return result of getClosestPoint on collider. This method is called with the character's root transform position and the intersecting collider that start IK target position tracking receives as an argument. We'll need to add the root transform as a variable in the context, and add it as an argument when the context is instantiated. Then create a public getter so that it's accessible throughout our state machine. and of course, actually pass the transform route in the instantiation. Now, whenever start IK target position tracking is called, we expect the current side and associated variables to correctly update. Let's try placing a log in the left and right side conditional blocks to test out our method and see if it works. Our reset state is not going to use any of the onTrigger callbacks, but the search state will. For now, let's have the reset state immediately return the search enum. This causes our state machine to immediately switch to the search state the first time update state is run. And now we can call start IK target position tracking in the onTrigger enter method of the search state. Entering play mode, we can now see that as the character approaches the colliders in the environment, the right and left side are correctly being logged. However, when our character is moving in a dense environment, chances are that the trigger will intersect with many colliders. Ideally, we filter for objects we want to interact with using a layer like interactable. In the start IK target position tracking method, we'll wrap our logic in a new if statement. The intersecting collider provides access directly to its layer through its game object. Using Unity's layer mask and its built-in name-to-layer method, we can ensure that our logic will only be run if the game object has its layer set to interactable. Now, we just need to create and set this layer name for the game object that we want. In play mode, we'll now see only the interactable layer will be logged. But as the character moves around, it's also possible there are multiple objects with this layer. This would restart our procedural animation cycle over and over again. To fix this, add another public variable in the context titled current intersecting collider of type collider. Then, add a check that current intersecting collider is equal to null after the layer validation. Now we just need to set the current intersecting collider at the top of start IK target position tracking method. This ensures that once the procedural animation starts, it won't transfer to another collider. And to reset this value, let's implement reset IK target position tracking. Validating that the exiting collider argument is equal to the current intersecting collider, we can set the current intersecting collider back to null. Let's try testing our implementation again by adding the call to reset IK target position tracking in the onTrigger exit method of the search state. In our Unity scene, first create the interactable layer. Then we can add a few game objects and mark them with this layer. Entering play mode, and now, as the character moves around the environment and the trigger collider enters and exits the interactable colliders, we can see the logs showing up in the console. Okay, we are able to accurately determine the correct side for our character's procedural animation. Now we want to calculate the closest point on the stored collider from that side's shoulder. Using the shoulder gives us a reliable and natural result when we reposition our IK target. In the environment interaction state, let's create a new method, setIKTargetPosition. This method will start by setting a new variable, closest point on collider from shoulder, which we'll store in the context with a default value of vector3.positiveInfinity. This variable will be equal to the return value of getClosestPoint on collider, passing in the context current intersecting collider. Now we could just pass in the current shoulder transform position that's stored in the context as the second argument, because we know that's the current side's shoulder position. However, let's use Unity's built-in debugging gizmos to visualize the problem with this vector3. To showcase the problem, call setIKTargetPosition at the bottom of startIKTargetPosition tracking method, and in a similar if statement for the updateIKTargetPosition method, validating the intersecting collider argument is the same as the stored collider. Be sure the search state now calls startIKTargetPosition tracking, updateIKTargetPosition, and resetIKTargetPosition tracking in the respective onTrigger callbacks. Then, in the environment interaction state machine, let's add the onDrawGizmoSelected method. Inside this method, set the gizmo's color to red and add a conditional statement. If the context exists and the closest point on collider from shoulder variable is not equal to null, then have the gizmos draw a sphere at that position with a small 0.03 radius. Testing in play mode and moving to an interactable surface, we can now see the closest point from the shoulder position is rendering from the gizmo. Awesome! However, there is a problem, the y-axis. As our character moves, the shoulder height is not always the same. This can lead to issues down the line when we determine if the character is getting further away from the interactable surface and we're trying to understand if we should reset the animation. To prevent this from becoming a problem, let's store the shoulder height separately one time. An easy place to do this is in the context constructor. Here we can set a new variable, character shoulder height, and we can set it to either the left or the right root bone's Y position. In our set IK target position method, instead of passing in the current IK constraint's root bone position, we'll use a new vector3 which extracts the X and Z positions from the current IK constraint's root, but uses our new character shoulder height variable from the context as the Y value. Entering play mode, and we can now see that the Y position at the closest point is consistently at the same height. Nice. But what happens when we exit the collider? We need to reset the closest position. In the reset IK target position tracking method, we'll set the closest point on collider from shoulder variable back to positive infinity. Now that we have the closest point on the collider from the character shoulder, we can start to calculate the placement for the IK target of the current 2-bone IK that's in use. You may think that we can just set the current IK target transform equal to the stored closest point. However, doing this clips the character's hand right through the interactable surface. What we need to do is add an offset to bring the hand closer to the character. Let's start with the direction. In the set IK target position method, create a new vector3 ray direction and set it equal to the current shoulder transform's position minus the closest point on collider from shoulder. This provides us with a new directional vector that points from the stored closest point in the direction of the character's shoulder. We'll normalize this value to create a unit vector pointing in the correct direction. Next, we'll create a float titled offset distance and set it equal to 0.05. The offset will be equal to the normalized ray direction times the offset distance. And finally, a new vector3 offset position. This will be set to closest point on collider from shoulder plus this offset value. To piece it all together, set the position property of the current IK target transform, which we know as the red blocks in the editor, to this variable. We'll come back to this final assignment later on as we explore each state, but for now, we can test our current implementation in play mode. As the character approaches the wall, the current IK target snaps to the closest point. But nothing else happens. A core piece of any rig are the constraints' weights. Thus far, we haven't made any changes to the weight in our code, but programmatically updating the weight is an important part of the environment interaction state machine. To showcase the work that we have done, here's what happens when we have the weight set to 100 by default from the inspector. The IK constraint clearly overrides the movement of our character's arms. But as we approach the wall, we can see the current IK target snap to the point on the wall. So far, so good. Our next and final step is to program each concrete state's implementation and get our procedural animation to look a little more natural. Taking a look at the state machine's wire mock, each concrete state derives from the environment interaction state that now provides the ability to track the closest position to the interactable wall or surface. There are also 5 concrete states, each of which implement the abstract methods from the base state, inherit the methods from the environment interaction state, and define the constructor that helps the state machine properly store the state behind its associated state key enum. We've made some small changes in some of the concrete states up to this point. Now, let's review and make some necessary changes to all of our concrete states. This step is crucial in order to create a more natural and realistic look for our procedural animation system, and it will allow us to reset the state machine so it can be activated and deactivated more than once, just like in Uncharted. We'll end up coming back to each state multiple times as they get more complex, but let's start with the initial state of the environment interaction state. Open up the reset state file. The purpose of this state is to temporarily deactivate and reset any procedural animation logic. Right now, its getNextState method immediately returns the search state from our previous testing. But in practice, there should be some delay between when the character enters this state to deactivate the procedural animation and when it reactivates and starts to search for interactable surfaces again. Let's add a new float member variable, elapsed time, with the default value of 0. In the reset state's update method, we can go ahead and increment this value by time.delta time so that it increases in real time. This enables us to add a condition in the resetState's getNextState method that only switches to the search state if elapsed time is greater than a specified amount of time. We'll call this variable resetDuration, and it is a value that I recommend you test out to feel what makes the most sense for your character and game. But I liked 2 seconds. Elapsed time starts with a default value of 0 the first time that the reset state is used. But when it passes the duration threshold and switches to the search state, the value of elapsed time remains greater than that duration. This means that when the state machine switches back to the reset state, it would immediately switch to the search state once again. To fix this, we can set the elapsed time back to 0 in enter state, ensuring that the timer starts over. There are actually a few variables that we should ensure are correctly reset at some point in the reset state. Closest point on collider from shoulder is expected to have already been reset to positive infinity in the reset IK target position tracking method of the environment interaction state. For reassurance, let's add that in the enter state method as well, just to be safe. And the same thing for current intersecting collider, set that to null. Before the reset state transitions to the search state, add one more condition that validates that the player is moving. Accessing the context stored rigid body component, set a variable is moving to the rigid body's velocity not being equal to vector3.0. Now we add this as a condition to switch to the search state. Let's see if the delay is working as expected. I've added a log to the enter state method of the search state. Testing in play mode, and we'll see that after 2 seconds, the search state log hits our console. Success! We will return to the reset state as we flesh out the other concrete states. So for now, let's move on to the search state. The search state is the stage in our procedural animation cycle where the character is able to start interacting with a surface. For this reason, it is the first state where we use all 3 on-trigger callbacks. This means we need to call the start IK target position tracking, update IK target position, and reset IK target position tracking method in its associated callback and pass through the collider argument. For the search state, there won't be any changes necessary to the IK constraint's weight. This is because the search state doesn't actually show any visual changes to the player. Its purpose is only to determine if a character is close enough to a surface for the procedural animation to begin. So how do we know when the search state should transition to the approach state? We will calculate if the character is within a certain distance threshold. In the getNextState method, create 2 Boolean variables, is close to target and is closest point on collider valid. And at the top of the file, create a new variable, a float approach distance threshold, with the default value of 2. Using this variable, we can set is close to target to a distance check between the closest point on collider from shoulder and the character's root position, validating that it is less than the new threshold value. And is closest point on collider valid will check if the closest point on collider from shoulder value is not equal to positive infinity. Using these 2 variables, we can conditionally gate the transition from the search state to the approach state. And now, the search state successfully tracks the closest point using the callbacks we set up earlier, and will transition to the approach state when the character is close enough to the interactable surface. The approach state is the first state where the current IK constraint's weight will be increased. This will make the procedural animation visible by partially overriding the character's keyframed animations. Let's open up the approach state. In this file, all 3 callbacks will be set up the same way as the search state. This will allow the state machine to continue updating the IK position. To update the weight of the closest side's IK constraint, we can access the weight property of our current IK constraint variable stored in the state machine's context. If we set this to 1 or 100% in the enter state method, in play mode, as our character gets closer to the interactable surface and enters the approach state, the hand immediately snaps to the target position. Awesome, but there are a few things that we should change. Ideally, this transition is updated over time. We can use the math_lerp method, aka linear interpolation, in the state's update method. Lerp accepts 3 parameters, a starting value, a goal value, and the interpolation value, a value between 0 and 1. What's returned from lerp is a value between the starting and goal values using the interpolation value as the percentage between the two. In update, set the current IK constraints weight equal to the lerp method, passing in the current IK constraints weight as the starting value, a variable approach weight as the goal value, and elapsed time over lerp duration to create a fraction between 0 and 1. At the top of the file, we can add all of these new variables, setting the default value of elapsed time to 0, the lerp duration to 5, and the approach weight to 0.5. Like the reset state, we'll reset elapsed time back to 0 in enter state, and increment it by time.deltaTime in update. Testing in play mode, as the state machine transitions from the search state to the approach state, the procedural animation now gradually overrides the character's hand. Because the goal weight was only 0.5, it's a hybrid between the keyframed animation and the target position from the IK constraint. When comparing our approach state to the Uncharted example, the placement of the hand is seemingly much higher in our version. To fix this, we're going to move our target. One of the beautiful things about breaking this project into a state machine is that we can have dedicated logic for each state. For the approach state, let's find a way to set the Y position of the IK target to a lower value. We can later dynamically raise the target's Y value in the rise state. In the context file, create two new variables, a float interaction point Y offset with a default value of 0, and a float collider center Y. Shifting to the construct environment detection collider method found in our environment interaction state machine file, we'll set the context new collider center Y variable equal to the root collider center Y value. This happens to be the perfect height for the approach state's hand position, and if you skip making this method, you'll want to find the Y value that's about waist level for your character. In order for this to work, we need to set the interaction point Y offset to the collider center Y value. Opening the reset state file, set the interaction point Y offset equal to the lerp value of the current interaction point Y offset, collider center Y, and elapsed time over the lerp duration. Add the lerp duration variable to the top of the file, this time set to 10. Now we just need to ensure that our IK target is using the new Y offset value. Remember, we used the set IK target position method to correctly place the position of the IK target. All we need to do is replace the Y value of the vector3 argument with our new interaction point Y offset variable, and that will correctly set our current IK target transform's position. Testing again in play mode and moving closer to the interactable surface, we'll see the hand raised to a waist level height. The approach state is almost complete. The remaining changes to implement include rotating the character's hand and updating the getNextState method to transition out of the state. For the hand rotation, we'll want the palm to point towards the ground. With the multi-rotation constraint added to both the left and the right arm rigs, we just need to update the rotation of the IK target and our constraints weight for this to work. We already have it so that each palm points in the Z forward direction of the target. So we just need to rotate the IK target so that its Z forward is pointed down. In update, create a new quaternion, expected ground rotation. This will be set to a method call to the quaternion's lookRotation method. Pass in a negative vector3's up property as the first parameter, and the root transform's forward property as the second. What this does is create a rotation with the specified forward pointing towards the ground and up pointing in the current forward direction. With this expected ground rotation variable set, let's access the current IK target transform from the context and set its rotation equal to quaternion's rotate towards method. Pass in the current IK target transform's rotation as the first parameter, the expected ground rotation as the second, and the third parameter we need to pass a value that dictates the speed of the rotation. Let's use a rotation speed variable multiplied by time.deltaTime, and define that float at the top with the speed of 500. This will now update the rotation of the IK constraint. However, if the weight of the multi-rotation constraint is at 0, then this new rotation won't be visible. Let's duplicate the lerp logic we used for the IK constraint weight, but instead we'll update the weight property of the current multi-rotation constraint. Then replace the second argument, the goal, with a member variable approach rotation weight. We'll define this with a value of 0.75 because we want the rotation to mostly override the keyframed rotation. Testing in play mode, and now the hand correctly raises to about waist height, and the hand rotates, pointing the palm towards the ground. Awesome! The approach state has two states that it can transition to: the rise state, or back to the reset state. Our procedural animation cycle transitions from the approach state to the rise state when the character is within a certain distance from the interactable surface. Previously in the search state, we validated the distance from the root transform to the closest point on collider from shoulder. But for the approach state, we'll validate a new comparison: is within arm's reach. Is within arm's reach, we'll use the vector3's distance method to compare the distance from the closest point on collider from shoulder to the current shoulder's transform position property. And it will validate whether the distance is less than a new stored variable, rise distance threshold. We can set that to a value of 0.5. And now for the transition logic. We'll reuse the is closest point on collider real logic from the search state, then check if is closest point on collider real is true, and the character is within reach, transition to the rise state by returning that enum. Great, but what about the reset state? It is apparent in the Uncharted example that if the player takes too long in this state, the procedural animation deactivates. We'll do the same here in the approach state by adding another condition, checking to see if the elapsed time is greater than the approach duration. We'll set this to a value of 2 seconds, and return the reset state enum if it's over the state life duration. We've modified the weights of our constraints. So what happens when the animation cycle returns to the reset state? We need to turn the procedural animation back off by turning down the weights. Fortunately, we know how to do this now. Simply duplicate the lerp logic from earlier in the reset state to update all of the constraint weights back to 0 as the elapsed time is incremented. In play mode, this throws an error immediately. This is because we have not set the current IK constraint's value until setCurrentSide is called from the context. At the bottom of the context constructor, we will call setCurrentSide and pass in vector3.positiveInfinity as the default value. In play mode, we can now see the procedural animation will stop overriding the standard animation when entering the reset state. But let's also reset the IK target back to its original rotation and original position. To do this, we'll need to store these original values of both the right and left sides. In the constructor of the context file, we can set two variables: left original target position and right original target position. They will be equal to the corresponding IK constraint target's local position properties. Then in the setCurrentSide method, we'll expose a new current original target position variable from the context and set it to the appropriate side. As for the rotation, we'll also expose a quaternion variable from the context, original target rotation, and set it equal to the left IK constraint rotation in the constructor as well. With these values stored, in our reset state, we can now lerp the target back to its original position in update. And we can rotate the target towards the original rotation value as well. For the rotation, we'll use Quaternion's rotate towards method, and define the rotation speed as a member variable of 500. Testing in play mode, and our reset state is complete. Now, let's get back to the rise state. When the state machine enters the rise state, there are a couple of visible changes. The hand rises and rotates so that the palm is pointed towards the wall. To raise the hand, we have to update the Y value of the current IK target. Remember, set IK target position now uses a separate variable, interaction point Y offset, to update the Y value of the IK target position. This variable is set to the collider center Y. In the rise state, we'll add the respective callbacks to the three onTrigger methods. Then using lerp, we can dynamically update the position of the interaction point Y offset from the collider center Y back to our goal height expected for the procedural animation, closest point on collider from shoulder, Y property. Creating elapsed time and lerp duration variables will default to 0 and 5 respectively. Be sure to increment elapsed time at the bottom of the update method. At this point in the procedural animation, their current IK constraint's weight should take control of the majority of the hand and arm. Let's use lerp again to raise the current IK constraint from its current value set in the approach state to a higher weight here in the rise state. Again, we'll use lerp to update the weight to a goal weight, rise weight, this time to a value of 1. And in the case that you didn't set the multi-rotation constraint's weight to 1 in the approach state, we can reuse this rise weight to set it to 1 as well. If we test in play mode and get close enough to the surface to trigger the transition to the rise state, we'll now see the IK target rise to the expected height. Awesome, but the hand is still pointed towards the ground from the rotation we implemented in the approach state. Let's get the hand to correctly touch the surface. Create a quaternion member variable, expected rotation, and a new method, calculate expected hand rotation. In order to find the correct rotation, we first need to find the normal of the surface our hand is trying to interact with. Unity's raycast can help us do just that. First, we'll find the direction of the raycast by taking the character's shoulder position and the closest point on the collider stored in our context. Subtracting the shoulder's position from the collider's position and normalizing gives us the direction vector. Using physics raycast method, we can pass in the starting position, the direction, a variable ray for our raycast, and a variable max distance, which we'll set to 0.5. We can use this to check if the raycast has hit anything, and if it does, we can access the normal. However, the ray technically can't hit anything, including the player. When using raycast, we can include an additional parameter called layer mask, which specifies the layers that the ray should interact with. Fortunately, we already have the interactable layer we created earlier. Create a new member variable, interactable layer mask, and set it equal to the getMask method of the layer mask class, passing in the string interactable. By providing this as an additional argument to the raycast, we can ensure that the raycasts only interact with the intended environment game objects. Now, typically an object's normal will point away from the collider, but the direction that we want for our hand is the opposite of that, so that the Z forward is pointed towards the object. We'll create a vector 3, target forward, which is the opposite of the hit point's normal. Next, we'll set the expected rotation variable equal to a new quaternion created by using the quaternion's look rotation method. This takes two parameters, one for the expected forward direction and one for the expected upwards direction. We'll use the target forward variable for the first argument and vector3.up for the second. Great. Calling this method an update will give us the expected rotation for the hand. Now all we need to do is use the quaternion's rotate towards method, like in the approach state, to set the current IK target transform's rotation. Again, we'll use the current rotation as the first parameter, the expected rotation as the second, and for speed, create a new rotation speed member variable set to 1000 and multiply it by time.delta. In play mode, we can now see that the hand rises and rotates so that the palm faces the collider. The rise state will transition to two possible states, the reset state and the touch state. For now, let's only worry about the touch state. To transition to the touch state, we'll validate that the distance between the current IK target transform and the closest point on collider from shoulder is less than a stored distance, touch distance threshold. We'll set this to 0.05. As a reminder, the current IK target transform is updated every frame in the update method, which is bringing its position closer to the closest point. What this means is that it's only a matter of time before the distance validation comes back as true. But we can also add a minimum amount of time before transitioning to the next state, adding a variable touch time threshold. When these are true, we'll return the environment interaction state touch enum, and getNext state will transition to the touch state. We'll come back to the rise state in a bit. Oh, but before we move on, let's quickly reset elapsed time in enter state. Now, let's take a look at the final concrete state, the touch state. The touch state will continue the trend of using the onTrigger callback methods and the three methods defined in the environment interaction state. Outside of that, the touch state's only purpose is to count down until it ends the procedural animation and transitions back to the reset state. Create an elapsed time variable. Reset it to 0 in enter state, and increment it in update state. In getNextState, we'll validate if the elapsed time has passed a reset threshold variable with a default value of 0.5. Then we'll return the eEnvironmentInteractionState reset enum. Finally, let's test the full procedural animation cycle in play mode. With the character selected, we can see that the environment interaction state machine correctly creates the trigger collider. As the character approaches the interactable surface, we can see the search state transition to the approach state, partially raising and rotating the hand with a mix of keyframed and procedural animation. When the character gets closer to the surface, the approach state transitions to the rise state, smoothly interpolating the Y value of the IK target to the closest point on the surface from the shoulder. This raises and rotates the hand so that the palm is pointed towards the interactable surface. The rise state immediately transitions to the touch state, where the IK position is maintained for a short duration. And finally, the reset state takes over one last time and smoothly blends the IK position back to its original position. Awesome job. Here's what it looks like in real time. There is one more piece to our environment interaction state machine, which is the original list of triggers that resets the animation at any point during the cycle. These triggers are as follows. Trigger 1, if the character stops moving. Trigger 2, if the character starts moving further away from the wall. Trigger 3, if the wall ends and there's nothing left for the character to touch. Trigger 4, if the angle between the character and the point of contact no longer makes sense. And all four of these should be used in every state except for the reset state, because whenever any of these conditions are true, the current state should transition to the reset state. Just like when we created shared methods for each on-trigger callback, we can create another method in the environment interaction state designed to check these conditions. Defining it here means that it can be inherited by all of the concrete states. We'll create a protected method, check_should_reset, which will return a boolean. Let's implement the first trigger, reset if the character stops moving. Because this project was created with rigid body character movement, we can simply create a variable, isPlayerStopped. For this, we'll check if the rigid body that is stored in the context has a velocity equal to vector3.0. If you're using an alternative form of movement, substitute your own validation for the character's velocity here. This indicates that the player has stopped moving, so we'll return true. The second trigger, reset if the character moves further away from the surface, is a little more complex. Let's create a new method, checkIsMovingAway, which returns a boolean. In this method, we'll start by getting the current distance from the target by using the vector3distance method. We'll pass it the root transform and the closest point on collider from shoulder variables as the arguments. In order to check if the character is getting further away from the target, we'll need to store the lowest distance and compare it to the current distance. Because this method is designed to be used in multiple states, we'll store the lowest distance in the context with a default value of infinity. If the current distance is lower than the lowest distance, they are getting closer. We'll set the lowest distance equal to the current distance and return false because it should not reset. If the current distance is greater than the lowest distance, then we'll reset the lowest distance back to infinity and return true so that the state machine will reset. Let's give the player a little wiggle room though and add a new variable, moving away offset, with a value of 0.005. When we add this to the isMovingAwayFromTarget comparison, it feels a bit better to the player. There's an edge case to cover so that we ensure that this method works as expected. At the top of the method, if the current intersecting collider is equal to null, that means the state machine is still searching for a new interactable surface. Remember, we set current intersecting collider to null in the enterState method of the reset state. Here, we can just return false because we don't want to continuously loop back to the reset state if there isn't a real lowest distance yet. All of these returns are wrapped in conditionals. Last thing to do is return false by default. In the check_should_reset method, set a boolean isMovingAway equal to our invoked checkIsMovingAway method. Now check_should_reset will return true if the player has stopped moving or if they are moving away. And to be sure that the lowest distance is always reset correctly, we'll set it equal to infinity when any of these reset conditions are met. Trigger 3, reset if the wall ends and there is nothing left for the character to touch, is actually mostly handled from our previous work. Reset IK target position tracking will clear the current intersecting collider when the colliders are no longer intersecting. What we can do is create a new member variable, should_reset, and we'll set it to true in the reset IK target position tracking method. At the top of the check_should_reset method, add a separate condition. If should_reset is true, then we'll set it back to false, but return true. This allows us to return early and skip the other conditions. But again, add the reset of the lowest distance here as well. With trigger 4, create another new method, checkIsBadAngle. The intention is to reset the procedural animation if the character rotates past a certain angle. At the top of this method, add a condition. If the current intersecting collider is equal to null, then return false. We don't need to perform this check if the procedural animation isn't active. To check if the angle is no longer valid, we need to get and store the direction vector to the closest point on the collider. We can do this by subtracting the current shoulder transform from the closest point on collider from shoulder that are both stored in the context. Next, get the current side's direction vector. This will be either the left or right direction from the root transform depending on the context's current body side value. With the direction to closest point and shoulder direction vectors, we can validate if the current angle is valid by using the vector3 dot method. The dot method gives us the dot product between two vectors. If the dot product is less than 0, that means that the angle is greater than 90 degrees and is no longer valid. Return this value to complete this method. In the check_should_reset method, let's add another new variable, isBadAngle, and set it equal to the invoked checkIsBadAngle method. Then add isBadAngle to the list of possible conditions that can have check_should_reset return true. The final condition we'll add is optional and was not a part of the original list of conditions. If the player jumps. For this, we can add a check to see if the y velocity is greater than a certain threshold, let's say 1. Add isPlayerJumping to the list of conditions. Now check_should_reset returns true for any of the triggers we originally mapped out. And if none are true, the method should return false because the return type of check_should_reset is a boolean. With this complete, all we need to do is update our concrete state's getNextState method and add check_should_reset as a condition to return the eEnvironmentInteractionState reset enum. This can be done in all states except for reset because we're already in the reset state. Testing in play mode and stopping the character, the procedural animation now resets. Testing again and moving away from the collider, and the state machine enters the reset state again. If the intersecting collider exits the trigger collider, reset IK target position tracking is called and the machine resets. And if the character rotates too drastically, the machine resets. Wonderful! In the case that you may have gotten different results, I think it would be helpful for all of you if we ran through each file of the environment interaction state machine's code. We have the reset state, the search state, the approach state, the rise state, and the touch state. We also have the environment interaction state machine, the environment interaction state, and the environment interaction context. And with that, the environment interaction state machine is now complete. Taking a look, and our work certainly captures the intention and feel of the original example from Uncharted. And of course, we can always refactor to make it even better in the future. but we can really celebrate our hard work. This was a complicated project. In addition to this awesome environment interaction procedural animation, we built a strong foundation in our state machine code using best practices that allows us to develop more systems just like it in the future. The time and effort we put into developing the state machine using abstract classes and generics means it's all reusable for more procedural animation state machines with different constraints and results. An hour and a half later, and a year and a half later in real time, our procedural animation is complete. I hope that you learned a lot along the way. I know that I did, and I'd even refactor some of the stuff that's in there now, but that is part of this journey. If you did learn anything from this video, please consider hitting that like button so that we can reach more developers in the game dev community. And if you'd like access to this project's files without actually doing the tutorial, you can grab the project over on Patreon. I do want to thank all my patrons for supporting this channel over that amount of time. I can't wait to share more content with you more frequently going forward. And a special shout out for my top tier supporters over on Patreon, TarotDev, Jupe, Peter Steiner, and Ricky. Thank you all so much for the extra support. I will be back soon with more videos and tutorials, again, hopefully on a more frequent basis. But that is all for today. Thank you so much for watching, and I'll see you in the next video.